Hello, I am Elaine Daniele, a chemical engineer at Petrobras. My three coworkers, Thiago, Otávio, and Tatiana, and I research about gas lift valve failure. And now I'm going to present the comprehensive approach to tackle systemic failure and gas lift valve in pre-salt wells. For this work, we analyzed 6 gas lift valves, as you can see in those pictures. All of them were removed from Santos Basin's pre-salt wells after failure. All 6 wells are natural flowing wells and produce an average of 70,000 barrels per day. So, if all are natural flowing wells, why did you use gas lift equipment? Because in 10 years, we expect to use them. And it's cheaper to install them in the first completion than to spend money in a future workover. 5 of these gas lift valves are a beta model and 1 is an alpha model. I'm going to show you the differences in the next slide. All of them were of the high reliability class, meaning that the liquid discharge capacity of all valves is 2 barrels per minute. These valves had been inside the wells for 4 years on average. The time for workover operation for retrieval of these valves are shorter than the initially projected forecast. What does it mean? More cost. In this picture, you can see how the valves arrived in the onshore laboratory after the removal workover. The gas lift valves of well A and B present different residues, although the wells produce with similar water cuts. On the other hand, it can be seen the well C, D, and E presented a black residue, and well F did not present any residue at all. Another interesting information is that both wells B and D produce the same oil field to the same production unit. However, they presented different residue. What happened in each case? Why did the well valves with similar characteristics generate different residues? Here, you have 2 examples of a high reliability gas lift valve, alpha and beta model. 2 key of the high reliability is the check valve. In alpha model, here on the left, the check valve has 5 parts. There are the ring, an elastomer, the check seal retainer, a metal, a check dart, a check compression spring, and a nose retainer. The 2 first parts make a double sealing system, elastomer metal and metal metal. Another part you can see here, and number 6 is the Venturi seat. Another time is the beta model, here on the right. The check valve has only 2 parts, the spring and dart, and dart is connected with Venturi seat. In this model, the dart and Venturi has a different design. Also, it's important to say, in this beta model, there is only metal-metal sealing. In both cases, when the spring is relaxed, the valve to remain in a closed position. Although, when annulus pressure is greater than tubing pressure, the spring is compressed, and the valve is in an open position. Now I'm giving you 2 more details on the well B case. In this slide, you can see the comparison of the internal components of the well B valve alpha model with those of unused one, a new one. You can notice the complete obstruction in the internal parts. Here is the annular flow entry, and here is the flow output into tubing. The same residue was found in the valve injection holes, which have direct contact with annulus fluid, and the valve nose, which has direct contact with tubing fluid. Here you can see in details the comparison of well B internal parts and the new valve parts. All dart holes are blocked, as like the nose retainer and the Venturi seat. After the initial completion, the well B annulus was filled with a packed completion fluid, up to 100 meters above the depth of the gas lift valve. The annulus above the packed fluid was filled with diesel, like is shown here. At this moment, the pressure at the depth of the gas lift valve inside the tubing were estimated at 394 kg-force per square centimeters, and inside the annulus at 210. This represents a differential pressure of 184 in favor of the closure of the valve. The test carried off 1,000 days after, the pressure in the tubing and the annulus became 290 and 300 kg-force per square centimeters, which reached a negative differential pressure of 10. This was a strong indication that while the well B was producing, the gas lift valve was open. So, why did the annulus pressures go up? Probably, when the well B was kicked off, the tubing pressure decreased after the flow started. Because of that, the tubing temperature increased, and, as a result, the annulus temperature also increased. There was only liquid inside the annulus, and the Christmas tree annulus valve was closed. Then, the diesel expansion results in the annulus pressure increase. When the annulus pressure became greater than the pressure inside the tubing at the depth of the valve, the gas lift valve opened, and the packed fluid met oil plus water. After pressure equalization, the well behaved like a U-tube. When and how was the valve failure discovered? In this chart, you have tubing pressure in dark blue, annulus pressure in red, Christmas tree tubing valve in yellow, and Christmas tree annulus valve in gray, and choke valve in orange. About the valves, when is it open, you have the value of 1 in the right ordinate axis. When it's closed, you have 0. Both Christmas tree valves have the same open and closed behavior. The annulus tubing communication was identified during an expected well closure event. In this moment, the weather cut was about 12. The annulus Christmas tree valve was open, and we expected that the tubing pressure would increase and annulus pressure decrease. However, as you can see in this chart, what happened was that after the closure of the well, the close of the choke, the tubing pressure in dark blue increased and the annulus pressure in red followed this increase until there was a pressure equalization. And there is another evidence of the hypothesis presented in the previous slide. A transient multi-phase flow simulation was performed considering the kickoff condition. The result is shown in this chart, where you have the pressure trend in the left ordinate axis, the flow rate trend in the right. The tubing pressure is represented by the blue line, the annulus pressure by the red line, and the gas lift flow by the purple line. The simulation showed an initial transient with high discharge liquid flow due to the large drawdown at the well kickoff. It showed that fluid flow was from the annulus to tubing. Also, the simulation showed the effect of the diesel expansion and the subsequent pressure equalization between the tubing and the annulus pressure, which indicate that gas lift valve was open. The simulation also showed that the liquid flow rate through the gas lift valve never exceeded 2 barrels per minute, which is the critical technical limit of this valve model. Now, I'm going to analyze the residue and composition of produced water and fluid. The residue found in well B gas lift were analyzed by X-ray diffraction, and the sample showed mainly strontium and smaller proportion of barium. The produced water contains barium and strontium in high concentration. There was sulfate too, like you can see here in this table. The packed fluid used in the well B was a brine of sodium chloride with a standard corrosion inhibitor. During a cover operation, to avoid rig downtime, it is common to use seawater instead of potable water in the formulation of completion fluids. Unfortunately, this brought to the completion fluid a high concentration of sulfate ions from seawater. It is believed that The strontium ions from the produced water match the sulfate ions from the completion fluid and generate the strontium sulfate. In the high pH value system, such as the completion fluid environment, the reaction is enhanced. The same is true for the formation of barium sulfate. The saturation index reached a right value, making a suitable condition for the scale deposition. We know that the mixture of seawater and produced water is considered the main cause of scale deposition in oil fields. Differences and similarities in cases of well B, A, and D. When the gas lift valve of those wells were analyzed, similar residues between at least two of them were expected, since the wells have several similar properties, like you can see here in this table. Well A and well D are a beta model, and well B is an alpha model. The water cut is similar in well B and well A. Another similarity is the fact that well B and D, although with different water cut at the time, are from the same oil field and produce to the same unit. However, the residue from these three valves presented different characteristics and only the well B gas lift valve presented the scale. The well D gas lift valve residue was composed mainly of iron with a small concentration of barium. Well A gas lift valve did not present residue on the outside of the valve frame. However, it was not possible to dismantle it. There was no tool for it in that time. Thus, it is very unlikely that no residue deposited in the internal of this valve, since it presented check valve stuck in an open position, like in this picture, and this indicates the valve failure. One possible cause of this type of failure is residue deposit in check valve. The composition fluid used in all three cases is remarkably similar. However, the well A was completed with nitrogen in the annulus, differently from well B and well D, that were completed with epoxy fluid and diesel. The fact that well A was completed with nitrogen in the annulus avoided contact the completion fluid with produced fluid, which would allow the formation of compounds that could be deposited and cause the valve failure. Conclusion. The facts that corroborated the deposit of the barium and strontium sulfates in well B and not in well A are the greater presence of ions in well B, the fact that well A was completed with nitrogen in the annulus, thus avoiding the mixture between the produced water and the completion fluid. The hypothesis that the failure of this gas lift valve may have originated in the well completion phase is weak, since the critical liquid discharge flow of 2 barrels per minute is considered to have been respected during this phase. There are indications that well B operated while the gas lift valve was open. It probably happened due to the contact between the completion fluid basic pH with high concentration of sulfate ions, and the produced water from the reservoir with high concentration of barium and strontium. Recommendations for upcoming workovers. It is recommended to study the viability of installing blind valves. This is especially important in wells where the gas-oil rate is expected to reach extremely high values, and thus make, even after the increase of water cuts, the use of artificial lift is unnecessary. It is also recommended to complete the wells placing nitrogen in the annulus instead of epoxy fluid and diesel. Thus, in case of gas lift failure, the contact between the epoxy fluid and the produced fluid can be avoided. Also, due to the expandability of the gas, it would be easier to maintain the pressure inside the annulus. Recommendation for wells and production. The pressure equalization between the annulus and the tubing at the depth of the gas lift valve does not guarantee valve closure. At least a differential pressure of 7 kg per square centimeters is required to ensure the closure of gas lift valve. Monitor the annulus pressure, repressurizing the annular volume when necessary. If the gas lift valve is already installed, check the absolute pressure and the differential pressure that the annulus is subjected to. There is a possibility that the valve is open, making possible the contact between the annulus fluid and the produced fluid, which brings a high scale deposition risk. Elaborate a flushing procedure with diesel as the first step after determining the annulus tubing communication. It aims to remove a small residue that can be accumulated in the valve, which may prevent the closure of check valve. Monitor the water cut growing wells with gas lift valve. It's important to ensure the right dosage of scale inhibitor. An improvement in chemical injection system would bring a great gains to the integrity of gas lift valves and other equipment. New studies and transient simulation are necessary to better understand the failure mechanism of the gas lift valves in well A and D. For the accomplishment of this work, the support and teaching of Daniel Maia were essential. The author thanked Petrobras for allowing the publication of this article. Thank you.